and welcome to Beyond the Gates. I'm Annette Kirkland, and this season we're talking about today, tomorrow, always. We will be highlighting how ERDC is delivering impactful solutions today, driving innovation for tomorrow, and prioritizing people always. From groundbreaking research to enduring partnerships, we explore the power of progress rooted in purpose. This morning, I'm going to be speaking with Dr. Lein. He's a research civil engineer with the ERDC Cold Regions Research Engineering Laboratory, otherwise known as CRREL, and we're going to be talking about frozen ground heavy loads inside ERDC's one-of-a-kind simulator. Good morning, Dr. Lein.
Good morning.
How are you this morning?
I'm doing pretty good. I'm excited to talk a little bit about our frost effects load simulator. So, yeah.
Well, how's the weather in New Hampshire?
Right now, it's probably the most beautiful time of year here. It's fall, and the leaves are falling down on the trees and turning all sorts of colors, and just beautiful up here. But soon winter will be upon us.
I've been there in December. I understand what winter is in New Hampshire for sure. It's serious stuff. It's serious stuff. So tell me about yourself, your background, and your role at ERDC.
Well, as you explained, I'm a research civil engineer. I've been here for about 8 years. I kind of focus on two main things here with my research at ERDC. I do a lot of geotechnical engineering, and with that, I do the pavement systems and foundations and things like that. But I also have another focus, which we won't probably touch much on this one, but I also work with engineering materials.
Mm-hmm.
And so I've done everything from like ballistic impacts on cold materials and alloys and, to frozen roads and frozen ground. And if anyone out there is looking for a place that's an absolute playground to come and work, this is it.
From A to Z, in other words, right?
Yep, A to Z. If you can't find something you're interested in here, you definitely can't find something you're interested in.
Well, what part of your background led you to where you are?
Well, the geotechnical engineering background is really what led me to apply here, and I got a position and then kind of worked my way up through to being a research civil engineer, and I've really enjoyed it and got to work on a lot of unique projects, and nothing's ever the same day to day, so it's a real challenge, and I like that.
That's great. That's great to hear. So, okay, we're here to talk about the Frost Effects Load Simulator, an incredible capability there at CRREL. What is it, and what makes it so unique and cool?
Well, the Frost Effects Load Simulator, which we usually call the FELS, is a brand new purpose engineered machine that is capable of testing the gamut of civil engineering infrastructure. So things like roadways, culverts, foundations, pretty much anything that you would leave in the ground and gets exposed to the weather.
Mm-hmm.
This machine is housed in our Frost Effects Research Facility, which is a facility that can get cold. We can also, spray snow and things like that in there. We can flood it, things like that. But when those two are paired together, they really make a unique kind of world-class simulating environment. So you can test this infrastructure, in the real world, or as close as you can get to the real world scenario.
Okay, so here we go. The simulator has a load capacity, I understand, of 125,000 pounds. That's pretty massive. So what types of vehicles and equipment can it realistically test under those conditions?
Under those conditions, it can test a lot of vehicles that are currently in our inventories.
Mm-hmm.
Our first test, one of them is going to be the P-8 aircraft loading on the front gear. The nose gear of that weighs or has a load of approximately 89,000 pounds. So that's a lot.
Right.
And so we're going to run that back and forth over a concrete test section, and we'll get into that here in a little bit. But that the military aircraft like that keep getting bigger and bigger, and to keep up with those, we need the ability to apply higher and higher loadings for test and evaluation of your infrastructure under those realistic conditions. I will let you in on a little secret, though.
I love secrets. Go ahead.
Yeah. So tomorrow we're going to begin upgrading this to 250,000 pounds. So
No way.
Yeah, we're a little over doubling the capacity there, or almost doubling the capacity. And mostly we're looking for, the loads of the future, things like rocket cargo and other static or dynamic loads that, exceed our capabilities so far.
Okay. That's pretty exciting stuff.
Yeah, I'm excited for that too.
Okay. So how does as we call it, everything is acronyms around FAILS, which is the frost load simulator. So how does FAILS help researchers study the impact of frost depth on pavement performance in a way that couldn't be done before?
Well, I guess I'll go to a little bit of background on this, and explain a bit about pavements and pavement systems.
Mm-hmm.
So pavements are a layered system, and all the materials really have to work together to create a strong pavement. So these systems then are put out into the environment all over the world, and are susceptible to, rain, snow, ice, pretty much everything that Mother Nature can throw at it. The soil layers and rock layers below the concrete and asphalt layers aren't bound together. The concrete or cement holds the concrete together, the oil holds the asphalt together. And so those are fairly strong and can withstand a lot of, tension forces, whereas the rock layers and the soil layers below that are weaker and they have voids and water can flow through them. And so that makes them a little bit more susceptible. And that's the condition in which it's critical to capture when you're doing design and evaluation, because those things can damage your pavement very quickly, especially if you're applying loads during those weaker seasons. Mm-hmm. So that's why that time period is critical to capture, and that's what we intend to do in the FERF with our fells.
Okay. You always have to start somewhere, right? So what is ERDC's first project with the FELS, and can you walk us through what's being studied in that project?
We're really excited about our first project with the FELS. We're going to do a side-by-side comparison with the P-8 aircraft. It's one of the Navy's aircraft, and it's a kind of cargo fighter, almost in between as far as loading goes. Mm-hmm. But we're going to do that side-by-side comparison to tune the machine. But, as ERDC, we always incorporate a research element into that. So while we're tuning this machine, we're also going to do some joint research. Okay. And so as pavements heat and cool in temperatures, they expand and contract. And when they do that, if the pavements didn't have joints in them, concrete especially, it'd build up thermal stresses within your slabs and start to tear itself apart. And, you get your cracking everywhere, which you really don't want. So to relieve those and control the cracking, we put joints in there. And so those slabs then start to work a little bit independent of each other. And so in this concrete test section, there are joints, some supported by dowel bars, mm-hmm. Some unsupported, and we're investigating how that load transfers from one slab to another, as it is trafficked and through its lifespan. And what we're trying to do is investigate the amount of movement that these pavement sections through the joints will experience as we traffic across them. Right. The more movement in these joints, they deteriorate quicker, and so they start to rub against each other, and then it lets moisture in, and then other environmental factors. You start to freezing, and those joints expand, and so they're a really critical part of the pavement system, and that's what we're investigating. And I guess who really knew joints are all that important, but they're critical.
Well, and then you talk about, the test sections have multiple layers and subgrade, base, and concrete surface. Why is it important to recreate those layers, and what are you trying to find out?
So these layering systems in pavements, they're really meant to mimic what is done in the field. And so, and I say the field, I mean, airfields and roadway systems, wherever you're at.
Mm-hmm.
And so we, in our FERF and underneath in our test sections, we recreate as best we can what's going to be present in the field conditions. So we'll mimic their concrete structure out there. So if they're using, like on an airfield, 3-inch large aggregate or large rocks in the concrete, we'll go and get that and place that in our test section.
Okay.
If you're going to use granite rock or maybe it's a softer rock, maybe dolomite or something like that,
Mm-hmm.
we'll go and get that to place in our test section, just so we have a realistic idea of how it's going to perform in that field location. And then down to the soil layer below that, maybe we're putting in, building on a clay or a silt or a sand or all sorts of different subgrades exist out there. And so for wherever these roads are going to be or airfields, we try to simulate that condition so that we get our test to match up as close as possible to the field locations.
How long do these tests usually last?
So some of these tests can last months. Some of them last considerably shorter.
Okay.
But generally, we try to do it in about 3 months.
Okay.
That way we can capitalize on the winter season, which is usually what we look to test here at the Cold Regions Lab.
Mm-hmm.
But also, we can get enough trafficking built up in that period of time to simulate a full lifespan of use. And so, we can go anywhere from up to millions of passes on, airfield infrastructure and simulate, what is going to happen to that during its lifespan.
So, you were talking about airplanes. So I've heard you're using the airplane wheels in the testing. What's that going to show you exactly?
Oh, I'm glad you asked about that. So the aircraft wheels, right now, our first test is going to be the P8, but we also have a 777, which is a cargo aircraft. We're also looking to get a fighter gear aircraft gear set here shortly as well.
Mm-hmm.
But aircraft tires have really high tire pressures. So fighter aircraft have, closer to that 300, 350 PSI, whereas your cargo aircraft are in that 200 PSI range. And to put that in perspective, the car I drove in today, has a tire pressure around 35 PSI.
Right.
So they're really high tire pressures. They apply loads really well to pavements. They also have some with higher loading with those, but they're super specialty aircraft. But that P8, the total weight of it is around 189,000 pounds. So these aircraft, the fighters and the cargo aircraft, create different failure mechanisms in the pavement. So I like to have the analogy, like a cargo aircraft acts like a rolling pin, where it kind of shoves the concrete or asphalt around and then rolls over it.
Okay.
Whereas the fighter aircraft, they're more like a pizza cutter. They go down through and they just try to cut through the pavement system because they're higher loading and higher tire pressure. And so smaller tires, and they just cut like a pizza cutter in that case. So the tires are very important to the type of failure mechanism you're trying to recreate in your pavement structures. Ideally, you have some idea of how many passes or landings of an aircraft that are expected at these locations, and then you can simulate that with your fells.
Okay. So, how do the results of this research feed into updating or validating modern design standards for military and civilian airfields? And how does our data translate to real life?
So the data generated in these tests usually you get like one data point for each, thickness of pavement and pavement system you're doing, and then you can validate how many landings or passes is what we always call them, that pavement system can hold. And then we put those points inside of our design program for the Department of Defense, which is called PCASE. Mm-hmm. And so that's how we use that. The civilian airfields do it very similar. They use a design software called Farfield, and that's how they do it. But either way, as best you can simulate the real world conditions with the loading and the pavement system, the better off and more valid those points are going to be. And when we get these points, recreating them is very hard. So we try to do it the best we can and make it as close we can to the real world.
Data is so important. Data and ERDC all go hand in hand. There's, it's all makes such a big difference for the nation.
Oh yeah, definitely. And we have sensors in that pavement system there measuring stress, we measure strain, mm-hmm. How the pavement moves, and then, the loading that's applied on it through the different layering systems too. So all of that generates data, and it will help us inform lifespan and different aircraft that can land on these pavement systems.
Fantastic. So what does all this mean for soldiers who have to work and move in really cold places?
Well, it really means they'll be safer. They can adjust their aircraft or, other infrastructure loading to the current environmental conditions. And in the very end, you also save, dollars, and your infrastructure is going to last a lot longer. That's really what it means out there for the people at work.
Well, are there any key takeaways you'd like our listeners to understand about this research?
Definitely. I think kind of the biggest key takeaway is you need to design and build your infrastructure to last for generations. Our airfields right now have been out there for longer than their design lifetime sometime, and to be able to do that for the next generations, you need to test and evaluate your designs in the conditions as close to the environmental conditions that are at that place as possible. And if you don't, it's going to shorten the lifespan of that infrastructure. If it's cold, evaluate it in the cold. If it's hot, evaluate it in the heat. Small changes right now in designs are definitely pay off for those who follow.
And technology is ever changing, is it not?
Definitely. Technology has changed so much in the past 100 years, or even our parents' lifespan.
Right.
They went from not having cell phones to now, and a lot of these technologies are catching up to that, and we're also getting smart infrastructure and things like that can help inform the designs of the future.
Well, is there anything else you'd like to add to our conversation today?
No, it's just really exciting to talk about the science and technology that goes into pavement systems, and there's definitely much more about it here at the ERDC, and we have a whole branch dedicated to it too that I work very closely with a whole lot. So if you're interested in pavement infrastructure, we have lots of experts here and can definitely help out.
Well, thank you, sir, so much. Thank you, Dr. Lein, for being on the show today. And thank you, listeners. And we will come back at you next week. Thank you for listening to Beyond the Gates.